Coulomb's law can be applied to any two charged objects that are attracting or repelling one another. So it's applied a lot in physics when looking at electrostatics to start to explain and understand electricity, and it is applied for every type of bond that we see. Here we're focusing on ionic. So the equation for Coulomb's law, once again, is the force of attraction, that would be our bond strength, is related to the size of the charges and the distance between them. As we specifically apply this to ionic bonding, it is the magnitude or the charge of the cation and anion that tell us Q1 and Q2. Our alkali metals are +1, our alkaline earth metals are +2. The +2 charge on the cation makes a larger value for Q, a stronger force of attraction, and therefore a stronger bond. The halogens are -1, the oxygen family is -2. The bigger your negative charge, the stronger the attraction, the stronger the bond. The distance comes down to radius again. Closer to the top of the periodic table is small atoms and ions that tend to have small radii, meaning those ions end up very close together. A low R squared value means a stronger force of attraction. Coulomb's law is probably the most common application question you are asked about ionic compounds. This shows up in multiple choice, but also, more importantly, in free response. So that connection of magnitude of charge and distance is very important because it helps us understand ionic compounds and also connects back to the periodic trends. And when we're understanding this, we've said that it's not the gaining and losing of the electron that is the bond. It is the attraction between the positive and the negative. So down here, we've got some pictures of ionic compounds. Cations with +1 or +2 charges, anions with -1 or -2 charges, and they arrange themselves so that the opposite charges attract. It is the positive to the negative that holds them together. The bigger the positive, the bigger the negative, the stronger that attraction. So it's not the losing or the gaining of electrons that necessarily is the bond. That has to happen first. And that's described through a process or through a number that we summarize, I guess, as lattice energy. Lattice energy is the equivalent of a bond energy for ionic. It's the energy of formation for when we make our structure out of gaseous ions. So we end up with an ionic solid, usually 1 mole of it, which means billions upon billions of cations and billions upon billions of anions in their gaseous state have combined to form that ionic salt or ionic solid. You're going to release a lot of energy. It's a positive value for this because we're thinking about, if I were to break this back apart, how much energy would that take? Sometimes we think about it in terms of a whole process or what all occurred here. When we connect this with thermochemistry and thermodynamics, a definition we use is the delta H, or the enthalpy of formation. That is how much energy is needed to make a compound out of each element in its natural state. So sodium is naturally a solid, chlorine is a gas. So I could make 1 mole of NaCl, and that would be a negative delta H. But that doesn't really describe the process by which this compound is made. We don't just have that sodium solid bond to a chlorine negative. We exchange electrons and then have ions attract. So the heat of formation, or enthalpy of formation, is important, but the lattice energy is a much more valuable number in terms of understanding the bond strengths. And that's what connects to Coulomb's law. So the process here is that the sodium has to become a sodium ion. The chlorine has to become a chloride ion. And then the sodium ion and the chloride ion will become a compound. Overall, some of these steps are endothermic, some of these steps are exothermic, but the formation of the ionic compound is always favorable or overall exothermic. So this bond energy or lattice energy is a favorable thing. The process here is shown kind of graphically, step by step. Sodium solid can be turned into sodium gas by subliming or adding the heat to change the state of sodium. That is endothermic. When sodium atom becomes a sodium ion, that is the ionization energy. We normally incorrectly say that sodium wants to lose an electron. In reality, sodium has an attraction for its electron, and to take that electron away, we have to put energy in. For sodium and the alkali metals, it's a fairly small value, which is why it's often favorable that it occurs. But to get from sodium solid to sodium ion, we put energy in. Chlorine would start off as a diatomic gas. I would need to turn that half mole of diatomic chlorine into individual atoms of chlorine if I wanted to make sodium chloride. That takes energy. We are breaking the chlorine to chlorine covalent bond. Then here we are taking a chlorine atom and turning it into a chlorine anion. In that case, we are looking at the attraction, or we are looking at the electron affinity. In this case, that releases energy. Most of the time, pulling that in releases some energy for most anions. Now I have my cation and my anion, and I release energy. So what's important is that there's a whole bunch of endothermic things that do happen here. Most importantly, the ionization energy is endothermic, but it is the making of the attraction or the bond that is favorable. Sodium wants to lose an electron because after it has lost its electron, we had to put in energy to do that. It is now able to form the bond, which releases a bunch of energy. These can arrange themselves in lots of different ways. Most of the time, we show a really nice pattern of sodiums and chlorides, but there are different formations of the crystal that can happen. The difference in arrangement is sometimes based on the size of the ions. It is sometimes based upon the charge of the ions, like this is +1, -1, and +2, -1. But depending how big our atoms and our charges are, they'll arrange themselves differently. But in all cases, they arrange themselves to maximize attractions between cations and anions and minimize the repulsion between like charges. So like here, our fluorines, we want those to not be too close together, but we do want them to be as close as possible to our calciums. And there's some very important properties that we need to know that we'll come back and explain more. But because of these strong attractions, ionic compounds tend to be solids with high melting points. All of the atoms are tightly held in place by this strong lattice energy. They have a brittle texture because of the arrangement necessary of cations and anions. As a solid, they are unable to conduct electricity because the electrons have been gained and lost and are now stuck in place within the ions, which are also stuck in place. How extreme each of these properties is based upon how strong those bonds are or our lattice energy, which all comes back to Coulomb's law.